Welcome back to the Deep Dive. Today, we are opening up the hood on a piece of technology that I think really truly changed the trajectory of computer vision. We are talking about CLIP.
Contrastive language image pre-training. It's a bit of a mouthful, yeah. But it's the architecture that essentially taught computers how to read and see at the same time.
Exactly. And look, if you are an engineer or data scientist tuning in, you absolutely know the pain of the gold label problem.
Oh, for sure.
It is the bottleneck that has plagued machine learning for, what, a decade? Let's say you want to build a system that recognizes different types of sushi for a smart checkout counter.
Right. The classic supervised learning nightmare scenario.
So what do you do traditionally? You scrape, I don't know, thousands of images of sushi, and then, this is always the painful part, you have to sit there or pay a whole team of people to sit there and manual label every single one. This is salmon, this is tuna, this is a spicy roll.
It is the absolute #1 bottleneck of supervised learning. And it's not just the labor, which is, it's expensive and it's incredibly slow. It's the rigidity of it.
Rigidity, how so?
Well, if you train a standard model like a ResNet on the famous ImageNet dataset, it knows exactly 1,000 categories.
1,000 buckets. That is it. That is its whole world.
Precisely. If you show it a photo of a generic dog, it's happy it has a bucket for that. But if you show it a specific breed that wasn't in those 1,000 categories, or, I don't know, an alien or an abstract concept like peace, the model just breaks.
It panics.
It does. It's restricted to that fixed set of predetermined numeric buckets. It tries to force the new thing into an old box, and the results are usually nonsense.
And that is why today's deep dive is so exciting. We are looking at the paper Learning Transferable Visual Models from Natural Language Supervision by the team at OpenAI.
Wow.
This is the paper that introduced CLIP. And the promise here is just massive. We are moving away from those numeric gold labels, class 402, and moving toward a model that learns from raw images and raw text found all over the internet.
It's what we call natural language supervision. Instead of telling the model, this image equals label 5, we are teaching the model to understand the actual relationship between an image and a sentence that describes it.
So our mission today is pretty specific. We aren't just here to hype this up. We are effectively doing a practical AI digest on this architecture. We are going to build a mental blueprint for this system. We're going to teach you, the listener, how to implement the architecture, the loss function, and the inference logic of a multimodal system.
And we really want you to walk away understanding how to build a system that can classify images it has never seen before. That's the zero-shot transfer capability. That's the magic.
Okay, let's unpack this. Here is our roadmap for the session. First, we're going to look at the intuition. Why are we fusing text and images in the first place? And why is web scale the answer?
Then we'll get into the nuts and bolts of the architecture, that two-tower design that I mentioned.
After that, we'll dive into the math, which is actually quite beautiful. We'll look at the contrastive loss function and that massive matrix that makes it all work.
Then we'll cover how to actually use it for classification with prompt engineering, which is a whole art form in itself.
And finally, we'll look at the trade-offs.
Yeah.
Because, spoiler alert, it is not perfect. It really, really hates counting.
It really does struggle with counting. It's a fascinating blind spot.
But before we get to the failures, let's start with the big success. Why the move to multimodality? What was the breakthrough insight?
Well, if we look at sources like the Salesforce research on multimodal AI, they make a very human point. You and I, we don't interact with the world just through text. And we don't interact just through static pixels.
Right, we see, we hear, we read. It's all happening at once.
Exactly. Multimodality is about mirroring that. It's about multimodal fusion, integrating these different data types, these different streams of information, into a single representation to achieve something closer to real-world intelligence.
And the big shift here isn't just the data type, it's the scale. Right?
Yeah.
Because we've had multimodal data sets before. This isn't the first time someone's paired an image with text.
Oh, absolutely not. But the scale is the difference maker. This is the data shift. In the old days, and by old days, I mean, maybe 2018, we relied on crowd-labeled data.
Like MS Koyo or ImageNet.
Precisely. And those are fantastic, high-quality data sets, curated by humans. But they're expensive to create, and they are limited in size. You hit a ceiling.
Yeah.
CLIP moves us to web-scale data.
Which is where the paper introduces the data set they call WIT.
Yes, WIT, web image text.
And the scale of this thing is just...
Yeah.
It's hard to wrap your head around.
It really is. We're talking about 400 million pairs of images and text that they collected from the internet.
I found a visualization for this in our notes that just blew my mind. If you were to sit down and look at these training images, just one per second, 24 hours a day, without sleeping or eating,
It would take you about 405 years to see them all.
405 years. That is the sheer volume of supervision the model is getting. It's like it's reading the entire internet's visual library with captions.
That's a good way to put it.
But here's the thing that I think trips people up, and I want to double-click on this. We have had image captioning models before. We've had models that try to look at an image and write a sentence. Why is CLIP different? Why didn't they just do that?
That is the efficiency insight. And it's crucial for any engineer listening who wants to build this. Initially, the researchers tried that exact generative approach. They used a model architecture similar to one called Vertex, where you show the model an image, say a photo of a cat, and you ask it to predict the exact caption word for word.
So you give it a cat picture and you want it to output the text. There is a cat sitting on a mat.
Exactly. But think about the internet. An image of a dog on a porch might have a caption that says, "Good boy." Or it might be the file name dsc005.jpg. Or it could be "My summer vacation." Or even, "Look at that beautiful sunset in the background."
Right. The capture isn't always a literal one-to-one description of the main object.
Not even close.
Yeah.
So predicting the exact words is incredibly difficult and computationally just prohibitively expensive. There are so many valid ways to describe one image. If the model predicts a cute pup, but the label is a small dog, the model gets penalized in that generative setup. It's trying to solve a problem that is way harder than it needs to be.
So they needed a different approach. They pivoted.
Precisely. They switched to a contrastive objective. This is the key technical unlock. Instead of predicting what the text is, word for word, the model just has to predict which text pairs with which image out of a big batch.
Ah, so it's a matching game, not a writing assignment.
Exactly. That sounds much easier, doesn't it?
That sounds a lot easier.
And it is, for the model. This single change yielded a 4 times efficiency improvement in the zero-shot transfer rate compared to their baseline bag of words prediction model.
A 4x improvement.
Yes. And that efficiency is the only reason they could scale this to 400 million images. If they had stuck with that old generative approach, we'd probably still be waiting for the training run to finish today.
Okay, so that's the why. That's the core idea. Let's get into the how. Let's build the architecture. We mentioned the two-tower design. What does that actually look like?
Right. Imagine 2 skyscrapers standing right next to each other. Tower 1 is your image encoder. Tower 2 is your text encoder. These are 2 completely separate neural networks, at least at first.
Okay.
The goal is for both of these towers to output a vector, basically a list of numbers, that represents the content. And the crucial part is that these vectors have to live in the exact same mathematical space, the shared embedding space.
Let's zoom in on the image encoder first. If I'm an engineer implementing this in PyTorch or TensorFlow, what am I actually coding up?
You have 2 main options that they explore in the paper. Option A is the classic, a convolutional neural network, specifically a ResNet 50 backbone.
A workhorse.
Absolutely. But, and this is a detail a lot of people miss, they didn't just grab a stock ResNet off the shelf, they modified it quite a bit. They used what are called ResNet D improvements.
Okay, ResNet D, what does that actually entail? What's the D for?
It refers to a series of tweaks, mostly to the initial layers, the stem of the network. It changes things like the stride sizes and the pooling operations to preserve more of the spatial information early on. They also added something called anti-aliased rec2 blur pooling.
That sounds complicated.
It basically means they are being very, very careful about how they downsample the image. Instead of just taking every other pixel, which can create jagged artifacts, they apply a slight blur first. It just helps the model not get distracted by aliasing and focus on the real feature.
And they changed the very end of the network too, right? The final layer.
Yes. This is a big one. Typically, a ResNet ends with a global average pooling layer. You just take all the features from the final map and average them together. It's simple, but you lose all spatial information.
You just smash it all together.
Pretty much. CLIP replaces that with an attention pooling mechanism. You can think of it as a single, lightweight layer of a transformer-style multi-head QKV attention.
So instead of just blindly averaging all the pixels together, the model gets to look around the image at the end and decide which parts are most important for building the final description, the final vector.
That's the perfect way to describe it. It weighs the features dynamically before compressing them into that final vector. It pays attention to what matters.
Okay, so that's option A, the souped-up ResNet. But transformers are eating the world, so I assume option B is a vision transformer.
You guessed it. Option B is the VIT, the Vision Transformer. Their implementation follows the original VIT paper pretty closely. Splitting the image into patches, flattening them, and feeding them into the transformer as a sequence.
Any special modifications there?
One small but important one. They added an additional layer normalization to the combined patch and position embeddings right at the beginning.
A small tweak.
Why bother? When you train on this kind of scale for this long, stability is everything. That extra bit of normalization just helps keep the gradients in check and prevents things from exploding. It's a practical engineering choice.
Got it. So that's the visual tower, the skyscraper for images. Now let's look at the text tower. What's processing the captions?
This is a transformer, and its architecture is very similar to GPT-2. For their base model, they used a 63 million parameter model. It has 12 layers and 8 attention heads.
Which, by today's standards, is actually not that huge.
No, it's quite modest compared to modern LLMs. It shows you don't need a trillion parameters everywhere.
And how are they handling the text input itself, the words?
They use byte pair encoding BPE for tokenization, with a vocabulary size of around 49,000. But here's a key constraint you need to know if you're building this. The sequence length is capped at 76 tokens.
76 tokens. That seems kind of short.
It is relatively short, yeah. But you have to remember, we are mostly dealing with captions, alt text, maybe short descriptions, not entire novels. For this data, 76 tokens is usually plenty.
And how is the text formatted for the model?
They bracket the text with a start of sequence token, SOS, and an end of sequence token, EOS.
And how do they actually extract the meaning of the whole sentence into one vector? Where does that come from?
They take the feature representation from the activations at the EOS token position, but at the very highest layer of the transformer.
Why the EOS token?
Because of the causal masking in the transformer, that final EOS token has effectively seen the entire sentence that came before it. Its representation becomes a summary of the whole sentence's semantic content.
Okay, so we have an image vector coming out of the left tower and a text vector coming out of the right tower. But they might be different sizes, right? The ResNet might output a 2048 dimensional vector. The text transformer might output 512.
Correct. And you can't compare apples and oranges. That's why there's a final crucial step, a projection layer. They take those raw feature vectors from both towers and linearly project them into that shared multimodal embedding space. They basically force them to be the same size, say 512 dimensions, so we can finally compare them.
And the paper makes a point about this projection being linear, not some complicated mini network.
Yes. And this is a really interesting design choice. Other contrastive learning methods, something like SimCLR, for example, often use a nonlinear projection, like a little multi-layer perceptron in between.
Right.
The CLIP team found that for this specific task, switching to a simple linear projection made no difference in efficiency or performance. So they kept it simple.
I love that. Occam's razor in deep learning. If the complexity doesn't add any value, just cut it out.
Exactly. It's a great lesson in engineering.
So we have our architecture, 2 towers, projecting into a shared space. Now we need to train it. We need to teach these towers how to align their outputs so that dog pictures land near dog text. This is where we get into the algorithm itself, the famous dollar times no matrix. Walk us through a single training step.
Okay, so ideally you want to visualize a grid. A giant checkerboard. Let's say we have a batch of $9 image text pairs, and in the paper, as we'll discuss, they use a massive batch size of 32,768.
Wait, 32,000? That is a massive batch. Most people listening are probably training with 32 or 64.
It's absolutely huge. It's a key part of the secret sauce. So you have roughly 32,000 images and 32,000 captions. This creates a matrix of potential pairings that is 32,000 times $32,000.
That's over 1 billion possible combinations in a single batch.
It is 1 billion potential pairs, but only the pairs on the diagonal of this grid are correct, right? Image 1 goes with text 1, image 2 goes with text 2, and so on.
Those are the ground truth pairs from the dataset.
Exactly. The null pairs on the diagonal are the real data, or the positive pairs. The goal of the training is to maximize the cosine similarity of those diagonal pairs. We want the vector for image 1 and the vector for text 1 to be pointing in the exact same direction in that high-dimensional space.
And what about everything else in that giant grid? All the off-diagonal stuff.
Those are your negative samples. Image 1 paired with text 2, text 3, all the way to text, 32,768. Those are all incorrect matches. The loss function tries to minimize the cosine similarity for all of those 10 to n incorrect pairings.
So for every single image in the batch, the model is trying to pull the one correct caption closer, and actively push all 32,767 wrong captions further away.
Yes, simultaneously. This is called the info NC loss, or sometimes a multi-class n-pair loss, and they do it symmetrically, which is clever. They calculate the loss looking from images to text, and then they do it all over again, from text to images, and they average the two.
Why do they need such a ridiculously huge batch size? Why not just do this with small batches? What breaks?
That's a great question. It's because contrastive learning lives or dies by the quality of its negative examples. If you have a really small batch, say 4 images, the wrong answers might be too obviously wrong.
Like a picture of a cat and the wrong captions are about a submarine, a car, and a planet.
Exactly. That's too easy. The model doesn't learn much nuance. It just learns that cats are not submarines, which, is a low bar.
But with 32,000.
When you have 32,000 random examples from the internet, statistically, you're going to get some hard negatives. You might have a picture of a spotted dog and another caption in the batch about a spotted cat, or a picture of a black car and a caption for a dark blue truck.
So it has to learn the subtle differences.
It forces the model to learn much finer, more robust features to distinguish those within the batch. It has to actually look at the details and understand the concepts, not just do broad category matching. It raises the bar for what counts as a match.
Right. There's one other tuning parameter in the loss function that is fascinating here. The temperature parameter. Usually temperature is a hyperparameter we just said, right? Like in the softmax function, it controls how flat or spiky the probability distribution is.
Usually, yes. You'd run a few experiments and pick the best one. But in CLIP, they did something different. They made it a learnable parameter. It gets optimized directly during training, just like the network weights.
So the model decides how confident it should be in its own predictions.
In a way, yes. It scales the logits, the raw similarity scores, before they go into the softmax. They initialize it to 0.07, which is quite small and makes for a very sharp, confident distribution. But they also clip its value so it can't get too large and cause training instability. It's another one of those smart, practical engineering choices.
And just to give listeners a sense of the compute power involved here, you are not doing this on your gaming PC.
Definitely not. The paper states that training their largest ResNet model, the RN50x64, took 18 days on 592 V100 GPUs.
592 GPUs running nonstop for almost 3 weeks? That is serious horsepower.
It's a massive engineering feat just to keep a cluster like that running for that long without issues. And they use mixed precision, or FP16, to save memory and accelerate the training. It was a huge undertaking.
But the result, the pre-trained model, is something we can run on our own machines. And that leads us to inference. This is the part that still feels like magic to me. We've trained this model to match images and text. But how do we use it to classify an image into a category it's never ever seen before? This zero-shot concept.
This is the most elegant part of the whole system. In a traditional classifier, the last layer of your neural network is a set of weights that you learn specifically for your classes. A weight for cat, a weight for dog, a weight for car. That layer is fixed. It's frozen.
Okay.
In CLIP, we don't have that last layer. We generate it dynamically on the fly.
The paper describes the text encoder as a hypernetwork. What does that mean in this context?
It means the text encoder generates the weights for our classifier. Let's use an example. Say you want to classify an image as either a Pokemon, a Digimon, or a Tamagotchi.
Okay, things the model has almost certainly never been explicitly trained to classify.
Right. It has no Pokemon neuron. So what do? You feed the text strings Pokemon, Digimon, and Tamagotchi into the text encoder. It spits out 3 distinct vectors. Those vectors become your linear classifier for this task.
They are the weights.
They are the weights. You then feed your image into the image encoder, get its single vector, and you just calculate the cosine similarity between the image vector and those 3 text vectors. Whichever is closest wins.
So I can literally invent a classification task on the fly. I could ask it to classify between happy paintings versus sad paintings versus serene paintings, and I don't need to retrain a single thing.
Exactly. You just change the text prompts and you have a brand new classifier. You are, in effect, programming the model with natural language.
But there's a catch, isn't there? The paper talks a lot about prompt engineering. We hear that term all the time with ChatGPT now, but it was critical here too.
It matters a lot. A huge problem is polysemy words that have multiple meanings. The classic example the paper uses is the word boxer.
Right. If I just feed the single word label boxer into the text encoder, what happens?
The model has no context. It doesn't know if you mean a dog breed, a person in a ring punching someone, or a type of underwear. The vector it produces will be this muddled average of all those different concepts it saw on the internet. It's not very useful.
So how do we fix it? How do we give it the context it needs?
We use prompt templates. Instead of just feeding the word boxer, we feed the full sentence a photo of a boxer.
That seems so simple. Does it actually make a difference?
It works surprisingly well. The paper found that just adding that simple phrase, a photo of a nepic, improved accuracy on ImageNet by 1.3%, which is a significant gain. It tells the model, hey, we are looking for a visual object. It helps it navigate to the right neighborhood in that massive embedding manifold.
And you can customize this for different tasks, right?
Oh, absolutely. This is where the engineering comes in. If you are classifying satellite imagery, a photo of a probably isn't the best prompt. You might want a satellite photo of a city or farmland. If you're doing OCR optical character recognition, they found that putting quotes around the number or word helps. A photo of the text 7, context is king.
So you're really just guiding the model into the right part of that massive learned space.
Precisely. And you can take it even further with a technique called ensembling.
Now, usually when we say ensembling in machine learning, we mean training 5 different models from scratch and averaging their predictions. But this is different.
Very different. This is prompt ensembling. You don't train any new models. You just ask the same model, the same question, but in many different ways. Instead of just a photo of a dog, you also ask a drawing of a dog, a sketch of a dog, a low-quality photo of a dog, a close-up of a dog. You might create 80 different prompts for the same concept.
And what do you do with all those different text vectors?
You run all 80 text prompts through the encoder, get 80 different vectors, and then you just average them all together. You use that final averaged vector as the weight for your classifier. It's like getting a more robust, well-rounded opinion.
And what's the payoff for doing all that extra work?
It's huge. On ImageNet, ensembling 80 different prompts boosted performance by another 3.5%. That is the kind of gain people usually spend months of architectural tuning to get. And here you get it just by being more creative with your text.
So putting it all together in terms of performance, how does CLIP actually stack up against the old guard, like a fully supervised ResNet?
It's incredibly impressive. On the ImageNet benchmark, CLIP matches the accuracy of the original ResNet 50, which is 76.2%, without using any of the 1.28 million training labels from ImageNet.
It did that purely zero shot.
Purely zero shot. It effectively matches the performance of a supervised model that was trained on 16 examples per class, which is called 16-shot learning, but it does it with 0 shots.
That is wild. It's matching a supervised model without ever seeing the supervision for that specific task. But, and there's always a but, let's talk about the trade-offs. Where does CLAP shine, and where does it completely fall on its face?
The major win is robustness. This goes right back to the gold label problem we started with. Standard models are brittle. If you train a model on beautiful, clean photos of bananas, and then you show it a child's crayon sketch of a banana, a standard model often fails.
It overfits to the photo texture. It thinks banana means yellow and glossy and perfectly lit.
Exactly. CLIP, on the other hand, is highly robust to this natural distribution shift. Because it was trained on the wild, messy internet, which is full of cartoons, sketches, rendered text, blurry photos, artwork, it handles those shifts naturally. The paper shows it reduces the gap between clean ImageNet accuracy and wild accuracy by up to 75%.
That's a huge deal for real-world applications where you can't control the input. If you're building a content moderation bot, you need it to recognize a drawing of a weapon just as well as a high-resolution photo of one.
Precisely. However, there are the gotchas, and they are significant.
Okay, let's hear them.
First, abstract tasks. CLP really struggles with tasks that require systematic logic or geometric reasoning. For example, counting. If you show it a picture with 4 apples on a table and use prompts to ask how many apples, it's basically guessing.
It can't count to 4. A system this powerful.
Not reliably, no. It's looking for the concept of apples. It sees appleness in the image. It doesn't have a built-in mechanism to sequentially identify and count distinct objects. It also struggles with very specific tasks, like distinguishing the distance to the nearest car in the kitty self-driving dataset. It's a semantic matcher, not a physics engine.
And then there is the famous MNIST failure. This one really surprised me when I first read it. MNIST is the hello world of machine learning, just handwritten digits 0 through 9.
It's supposed to be easy.
Right. A high school student can write a model that gets 99% accuracy on it in an afternoon.
And yet, CLAP only achieves 88% accuracy on MNIST, zero shot. A simple logistic regression model running on the raw pixels beats it.
Why? How can it recognize a complex scene with multiple objects but fail on a simple, handwritten number 7?
It's a data distribution issue, and this is a key lesson about all these large models. The pre-training dataset, that WIT dataset with 400 million web images, it just didn't contain enough examples of messy, handwritten digits. It has plenty of rendered text like on street signs or in memes, but not scribbles on a piece of paper. So for CLIP, MNIST is truly out of distribution.
So it proves that SLAPE isn't magic. It is still fundamentally bound by what it has seen during training. It hasn't learned the abstract concept of sevenness in a way that transfers to a totally new domain like handwriting.
Right, it's not actually thinking or reasoning in the human sense. It is pattern matching on a mind-bogglingly grand scale. But if the pattern wasn't on the web in sufficient quantity, CLAP doesn't know it.
And that leads to the other major limitation, data efficiency.
Yes. From a certain perspective, CLIP is terribly inefficient. It took 400 million images to learn things that a human child can learn with just a few examples. It is a brute force approach. If you are trying to learn a brand new visual concept that isn't on the internet, you can't just show CLIP 3 pictures and expect it to learn. You'd need to fine-tune it on a lot of data, which brings us right back to the original problem.
And there's also the issue of bias, which comes with scraping the whole internet.
A huge issue. Since the data is uncurated, it learns all of the social biases present on the web. Evaluations on datasets like Fairface show it makes classification errors related to race and gender, particularly struggling with the non-white category. It absorbs and reflects our biases back at us.
Okay, let's bring this home. We have covered a lot of ground today. We moved from gold labels to natural language supervision. We replaced the bottleneck of human annotation with the raw scale of the internet.
We discussed the architecture, those two towers, the image encoder, specifically that modified ResNet-D with attention pooling, or the VIT, and the text encoder, which is like the small GPT-2.
We broke down the algorithm, that giant null and dollar times no matrix, maximizing the diagonal, minimizing everything else, all driven by a symmetric contrastive loss.
And we talked about how to actually use it, zero-shot inference. Using the text encoder to generate your classifier weights on the fly, and using smart prompt engineering like a photo of A to get the best possible performance.
So what does this all mean for the listener, the engineer, or the enthusiast who's been following along?
It means the era of needing a custom hand-labeled data set for every single new object you want to recognize is, well, it's ending. If you want to build a search anything tool for your company's photo archive or a content moderation system that can adapt to new slang or new symbols instantly, CLIP provides the architectural foundation to do that.
You don't need to retrain the model, you just change the text prompts.
Exactly. It decouples the visual concept from the training data. It allows us to communicate our intent to the model in English rather than in matrix math. It bridges that gap between human language and machine vision.
So here's my final thought for you to chew on. The paper argues that this zero-shot performance is a much better, more honest measure of a model's true capability than the old way of just splitting data into train and test sets. If we stop training models to pass specific tests like the ImageNet test, and we start training them to understand general concepts through language, are we finally moving away from just pattern matching and toward actual understanding?
Or, given that it failed so spectacularly on MNIST simply because it hadn't seen enough handwritten scribbles, is this just pattern matching on a scale so vast and complex that it tricks us, the human users, into thinking it's understanding?
That is the question. Is it intelligence? Or is it just a really, really big lookup table?
I think the answer to that question is going to determine the next decade of AI research.
Thank you for listening to The Deep Dive. Go check out the paper. Try implementing that loss function yourself. It's surprisingly few lines of code. See what you can build. We'll catch you in the next one.